Hello, I welcome you all to this another interesting screencast. The problem reads, determine the maximum force P the connection can support so that no slipping occurs between the plates. There are 4 bolts used for the connection, and each is tightened so that it is subjected to a tension of 4 kilonewtons. The coefficient of static friction between the plates is mu s equal to 0.4. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have this interconnection here of 3 plates connected using bolts and nuts. And each bolt is tensioned to a maximum or to a force, not maximum, to a force, to a tension force of 4 kilonewtons. So there are 4 of them. So we need to multiply by 4, which is 4 by 4, gives us 16 kilonewtons. So this is how much these particular plates are held together. And the coefficient of static friction between the contacting surfaces between these particular plates is 0.4. Now we are being asked to determine the maximum force that this connection can support so that there is no slip. Alright? Very, very interesting. We are not even talking about the capacity of the bolts and so on, just the friction capacity, just friction capacity. All right, how much P can we carry? Okay, due to the friction capacity of these particular three plates that are held together by the 4 bolts. Very interesting, I think. Of course, direct, but quite interesting, Right, so this is what we have right now. If I was to just show, so we have some tension force, like of course the bolts are they've been tightened. All right, so we are tightening them, so they are tensioned, right? They are tensioned, but they are exerting a compression force, right, on the plates. But the bolts are experiencing some tension, right? They are experiencing some tension in them, right? So this is what is happening there. This is the resultant on the plates. Let me just say, draw the plates. Let me draw the plates. So let's say our plates are this thick. Let's say they are this thick, like so. We have one there. Let's say we have another one here. And then we have another one here. So there is tension in the bolts, but of course they are exerting a compression force on the plates. So let's say, like I was trying to draw, they are exerting a compression force on the plate. Okay, this is the result on the actual plate, on the actual connection. Okay, so this is what I was just trying to show. So here we are saying this is 2 by 4 kilonewtons, and also this one is 2 by 4 kilonewtons. This is also 2 by 4 kilonewtons this side, and also this one is 2 by 4 kilonewtons. Okay, and then the equivalent is going to be somewhere, let's say. So, and then we have a force. Let's say there we go. We do have these particular forces. So let's say we have a tension force this side. We have a tension force this side, and then we do have another one this side, and we have another one this side. Right. And then let's say we have let's say this is the centroid of our reaction force on the plate on one side, and then let's say the normal force, assuming the plates, we don't neglect the thicknesses of the plates, all right, but of course we can neglect them. So if we didn't neglect that, then we can say, let's say we have our normal force maybe somewhere there. Let me move this just a bit. I move it maybe to somewhere there. Okay, so I was saying, let me assume my normal force is here. Okay, my normal force is here, and the force is in that direction, therefore we expect my friction to be in this direction like so. And then I have also here the same reaction, this same normal force, and then I have this reaction like so. And also here I have a normal force, let's say in this direction like this. Okay, and then I have my friction in this direction, and the same normal force there like so, and then I have my friction in that direction like so. All right, you don't have to indicate all these so imagine, like I said, I'm just imagining the thicknesses are negligible. Okay, the thicknesses are negligible, and then here let me say I have my, this is where I have my force somewhere here. This is the reaction from the board. Okay, so let's say I have this one there like so. All right, so let's label this. So I have here my, like we said, summation of the tension force in the board, which the reaction is a compression on the plates. So this becomes 4 times 4, right? So this is just 4 times 4, which is equal to 16 kilonewtons. So this is 16 kilonewtons. All right, and all these reactions here, let's just call them as we call these as N, and then this one has friction force F, this one F, this one N, this one F, and this one F, and this is given as our P, and this is our P, this is our P over half, and also this one is P over half. This is P over half. Okay, all right, so here we go. And then of course this one I'm just calling it some distance x there, and also this one x. You don't have to show that. If the thickness is very negligible, then you can just neglect that. Okay, I'm just showing all this stuff. So we can have something like this. All right, so I'm just going to use one. I'm just going to use this one here, right? Okay, so for me here, a number of unknowns. For me, I have number of unknowns is equal to 1, 2, 3, 4. So I'll say 4. Okay, number of equations of equilibrium. I have 3. But like I said, I can still go ahead and work out this particular problem, okay? But for me to find the maximum, or for the equations to be equal to each other, then I will need to also employ the friction equation mu n, and this is just equal to 0.4 times n. So we know here to say our summation of forces in the y equal to 0, okay? Like I said, I'm just using one figure because these are all the same. I just have to draw all of them. Again, you don't have to draw all of them. So this is just n minus 16 equal to 0. Therefore, our normal force is equal to 16 kilonewtons. And then we have summation of forces in the x direction equal to 0. Okay, going in that direction, we want to find the maximum value of P that can be supported without slipping or carrying. Then we have minus P divided by 2 plus F equal to 0. But we know that our F is equal to 0.4 n. Okay, therefore our P is just going to be equal to 2 okay, times 0.4 n, and n is equal to 16 kilonewtons. Therefore P will just be equal to 2 times 0.4 times 16, so this gives us a 12.8 kilonewtons. So P max, therefore this is our P max. This is the maximum value that this particular connection can carry, okay, without slipping. And this is a impending motion problem, okay? So it means the moment we exceed 12.8, we go to 12.81, then slip occurs, or 12.8000001. The moment we just exceed it by whatever value, then slip occurs, okay? So that is the maximum that we can go, okay? And we cannot exceed that. Right. I think this is about it. Let me just outline this. I took a little bit of time drawing these free body diagrams. You don't have to take that long when you are working out this. You just have to work out this very quickly and then find the solution. Right. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.